Let's now continue on with our lessons on matrices. First, let's look at multiplication of matrices. Just recall the last lesson we talked about scalar multiplication. So if we have a matrix C, if it is multiplied by a number, all the elements in the matrix is multiplied by the number. Now, let's have a look at matrix multiplication. Let's consider A, which is a 2 by 3 matrix, and B is a 3 by 2 matrix. Let's see, how do we do multiplication of A times B? First, we look at the top row and the first column. That will give us the first number in the new matrix. So 2 by 1 plus 1 by 3 plus 3 by minus 10. Let's do it. You might actually want to follow me. That to this, 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 and this multiplied by this. Alright, add them all together, you get minus 25. Now, one number is done. Let's have a look at the next one. Okay, we are still looking at the top row, but this time it's the second column. See, this multiplies by that, this multiplies by that one, and finally 3 multiplies by 9. Then we add it all together. We get the new number, the next element in the new matrix, which is 27. Following the same style, we've got to look at the second row and the first column. This time, 1 to 1, 4 multiplies by 3, and 5 multiplies by minus 10. And therefore, we've got the third number in the new matrix. Finally, looking at the row, second row, and the second column. 1 multiplies by minus 4, 4 multiplies by 8, and 5 by 9. And that's it. We complete the new matrix. So, we can rewrite it in such a way. A times B, which is this matrix times that matrix, we get that. Alright, let's have a look at this. Pause the video for a while and try this for examples based on the information I actually just told you. Alright, let's work on these examples. So having a look at this, what can we do? We know that we have to start off with a row, one row and one column. So in this case, it's 1 by 2, okay, plus 3 by minus 1. Next one, 1 by 1 plus 3 by 4. Therefore, that is 1 times 2 is 2 plus 3 times minus 1 is minus 3. And 1 plus 1 is 1 times 1 is 1. 3 times 4 is 12. Therefore, the new matrix is minus 1 and 13. Okay, I won't bother doing this by hand. This is the one I've prepared earlier. Now, you should actually try all these examples, use your ClassPad calculator. I won't have time to actually show you the ClassPad calculator on this video, but you should learn how to use it. The next one, if you look at that, is a 2 by 2 matrix multiplied by a 2 by 2 matrix. So this one is 2 by 1 plus 3 by 1, therefore is 5. Next one, minus 1 times 1 plus 2 times 1, therefore is 1. This one, 2 times 4, plus, which is 8, plus 3 by 3, which is 9, 17, and so on and so forth. Now, these are the answers. Can you notice something? If I've got 1 by 2 times a 2 by 2, the end result is a 1 by 2 matrix. 2 by 2 times 2 by 2 is the 2 by 2 matrix. What about this? 1 by 2 and a 2 by 3, we got a 1 by 3 matrix. And if it is 2 by 2 and 2 by 1, it's a 2 by 1 matrix. Now, you notice that disappeared, you've got 1 by 2 matrix. 2 by 2 times 2 by 2, that actually disappeared, and it's a 2 by 2 matrix. 1 by 2 and a 2 by 3, that disappeared. The end result is a 1 by 3 matrix, and this one, the end result is a 2 by 1 matrix. So it is actually a good check. When you check, if you know the dimension of one matrix and the other one, when you multiply it, it's actually the row number and the column number of second one. Now, look at that. It is telling me that the column number of the first matrix must be the same as the row number of the second matrix. If the column number is not the same as the row number of the second matrix, you cannot multiply. So if this is a 1 by 3 matrix and there's a 2 by 2 matrix, it will not happen. The multiplication cannot happen. Or if this is a 2 by 1 matrix and this is a 2 by 2, again the multiplication will not happen. Alright, let's have a look at multiplying matrices and see whether it's commutative. Let's do this. We know we have worked out this is that. But what if we reverse it? We actually use this to multiply to that. If we have 1 times 2 plus 4 times minus 1, that actually gives us minus 2. Look, it's completely different. Same with the next one. 1 times 3 and 4 times 2, which is 8 plus 3, 11, different from there. So in matrix multiplication, AB is not the same as BA. Therefore, matrix multiplication is not commutative. Now, this is extremely important. Two matrices can be multiplied together if the number of columns in the first matrix equals the number of rows in the second matrix. Back to my previous example again. This is what I say. Number of rows has to be the same as number of columns in the second matrix. Number of rows in the first matrix has to be same as the number of columns in the second matrix. If not, no multiplication could happen. Now, if matrix A has dimension of n times n and matrix B have dimension of p times q, the matrix products AB, which is that, the m times n matrix and the p times q matrix, can only be formed if n equals to p. And AB will have the dimension of m times q. So n and p will have disappeared. So the matrix product of B times A can only happen if q equals to m. And AB will have the dimension of p times n. In the product of AB, B is pre-multiplied by A, and A is post-multiplied by B. Okay? Because B is after A, therefore A is the pre-multiplier. Now, let's have a look at some practical example of a matrix. In this matrix, we know that we were told that there are competitions between 5 schools. And these are the number of first place, second and third place each school actually gets in that competition. With the first place, 3 points is awarded to the school. So, school A will have 3 points, plus 2 points, plus 1 point, 6 points altogether. Now, we can put this in actually a matrix form. This is actually the number of school and the number of places they got. And that is the point, first, second, and third. So, if you do a matrix multiplication, you've got 5 by 3 and 3 by 1. Therefore, the end result is a 5 by 1 matrix. 1 times 3 plus 1 times 2 plus 1 times 1 gives you 6. Second row, 3 times 3, 9, plus 1 times 2, 2 gives you 11, and so on and so forth. So this is actually very useful. In the final part of this lesson, we'll look at a couple of different matrices. First is a zero matrix. All elements in a zero matrix is 0, and the letter O is used to represent a zero matrix. So for any matrix A plus O equals to A, and O plus A equals to A. And O in this case is referred to as additive identity matrix. O is a zero matrix, A times O is O, and O times A is O. Note, however, if X and Y represents number, if X, Y equals to 0, then X equals to 0 and or Y equals to 0. But for matrices, if AB equals to 0, it is not necessarily that A and or B equals to 0. Have a look at this example. A and B, they are not zero matrix, but the multiplication of it, we actually got zero matrix. Now, another one to note. If X, Y, and Z represent numbers, if X, Z equals to Y, Z, and Z is not 0, we know that X equals to Y. But for matrices, if AB equals to CB, and B is not 0, matrix A is not necessarily the same as matrix C. Look at this example. We've got A, B, and C. A times B give us the matrix of 1, 9. C times B gives us a matrix of 1, 9. But A, is it the same as C? No, it is not. So be very careful when you're doing matrix operation. Last but not the least, we are looking at multiplicative identity matrices. In this case, it's actually a square matrix with the leading diagonal of 1. The elements in the leading diagonal is 1 for a multiplicative identity matrix. So, if I, M times N is a multiplicative matrix, I times A equals to A. And therefore, M has to equals to N. Same as well, B times I equals to B. Again, that proves that M equals to N. So I, the multiplicative identity matrix, always have the leading diagonal as 1 and is always a square matrix. Now, last thing for you to note in numbers, if x, y equals to x, for all x which is not equal to 0, then y is definitely 1. But for matrices AB times B, B is not 0, A is not necessarily equals to 1. Look at this. A times B, we get B, but A is actually not 1. This is the end of lesson 2. We'll look at matrices and root information in the next lesson.